Hello, Fiveable. This is Shane coming at you with the AP Stats sessions. Like I said, my name is Shane. I'm hosting the AP Stats sessions all year long. AP Stats was one of my favorite classes growing up. Still is. I love teaching it to my juniors and sophomores here in Oakland. So hang tight, and I'll walk you through AP Stats this whole year and get you those fives to save you lots of money on college tuition because it's just out of control these days. So let's get started. Today we're going to focus on still probably the second chapter, depending on where you are and what textbook you use. But I would say most students right now are probably in the normal distribution chapter or linear distribution. So let me know where you are. You can comment below or send me a message on the Fiveable platform, whatever it is, send emails so that we can get this geared to what you want and what you need. Today we're going to focus on the normal distribution, assessing normality. So how do we know if something is normal? We've been spending a lot of time focusing on normal distributions and doing some calculations like z-score with normal distributions. But how do we know if something is normal or not? Because if something's not normal, we can't continue with those calculations. Stop and do something else. Throughout the video, I'm going to be taking some drinks of some water or sparkling water. I apologize. I taught all day today, and it was our block day. So did a decent amount of talking. I don't like to talk too much because I feel like stats, in order to understand it, you have to do it. So I'm going to encourage you to get out your graphing calculators now. If you don't have the TI-84, it's something you definitely want to get before the test because it'll save you lots of time on the AP exam, especially on the free response part, something you're going to want to have because time is always the issue for the free response part of the AP exam. All right. And as always, if you have any questions below, if you have any questions, pop down below and use the Ask a Question feature. That's a really beneficial feature for me and you because it'll give us the ability to tailor this to your questions. Okay? So, as always, I go live Thursdays at 5 p.m. Eastern Standard Time. That's the best time for me. If something's not working for you guys and I get an overwhelming support for a different day and different time, depending on my schedule, I can definitely make that work. But you could always watch the replay. However, I think the benefit of this platform and this feature for you all is to ask the questions. So I'm going to highly encourage that you attend the live sessions because those are the sessions that you can actually ask questions. So if you are confused, instead of just rewinding the video and hearing the same thing over and over again, you can stop, ask a question, interact with me in a way that's going to better your understanding. As always, we're going to give you some exam tips. We're going to give you some FRQs, multiple choice, calculator tips, just it all. We're going to get you ready for AP Stats come May. First major topics that we covered: exploring data, designing studies, and the normal distribution. It's usually the first three that teachers teach. Some teachers don't do the designing studies unit. However, in talking to other stats colleagues over the past couple of years, they found that the designing studies coming first or second is super important for kids to better their understanding of the material. All right, so the normal curve, that's what we've been focused on this whole 2-3 sessions. But today we're specifically going to focus on how to assess normality. So one, why is a normal distribution, or why do we have to check a normal distribution for normality? Next, ways to check it. So how do we check if something is normal? Practice with data. So we're actually going to practice with some data to see if something is normal. And then we're going to do an FRQ. So an actual AP problem that has to deal with normality and normal distributions. So first topic, let's dive right into it. Why a distribution has to be checked for normality. So why even bother checking something for it to be normal? Well, we have a couple things. First, the normal distributions provide a good model of real data. So a lot of data that we collect will actually be normal. Not perfectly normal, because that's really, really tough to do, but it will be approximately normal, like test scores or heights of high school students or the amount of Snapchats someone sends in a day, right? We could probably get a normal distribution for the number of Snapchats a user sends in a day. And I bet Snapchat probably runs that data where we have, okay, here's the normal curve. We have some extreme outliers over here, extreme outliers over here. But most of our users are sending this many Snapchats in a day. And then they can kind of tailor their product to that. Not only Snapchat, but definitely other companies are using statistics to better their product, and make more money. But if something is not normal, we can't do the normal calculation. So that's why it's important that we check the conditions for normality, or check to see if a distribution is normal, because if it's not, then we can't use those same empirical rule. We can't use z-score. All these things that we use to break down data and distributions, we can't use if it's not normal. Okay, so the first way to check normality is the normal probability plot. So the normal probability plot is a graphical technique to assess whether or not data is approximately normal. And so you're going to see the plot over here on the right. If you plot this, and I'm going to show you how to do this on the calculator, but if you plot and you notice that it looks like a straight line, that means that the data is normal. So this data we have here is going to be normal data because it follows a linear pattern. Anything that deviates from a linear pattern is considered not normal. So it's either skewed or some other distribution that might take place, other shape, I should say. So you want linear when you check. Straight line is normal. Again, that's what we want. On the AP exam, I've yet to see a probability plot on there. I'll double check that and get back to you guys next week, but I can't recall the last time I saw a normal probability plot on there. Now they do ask you to check if something is normal, and we'll see that in the AP problem, but a normal probability plot, I don't know if I've seen that on, especially a multiple choice. Can't tell you last time I saw that. So something like this, we can clearly see, is not normal, right? So we kind of see a concave up. And so because that doesn't follow the straight line, this distribution would be considered non-normal. Pretty easy to see. A couple other ways to check normality. One is if you actually plot your data. So if you plot a dot plot, histogram, stem plot, box plot, if you use any of these can help you determine if something is normal. And what you're looking for is something that's roughly symmetrical, with most of the data concentrated on the inside. And so I'm going to show you using our document camera what that might look like. So let me go over to my document camera to show you. It doesn't tell you exactly, so we want to be careful, but it will show you, it will give you a good idea if something is normal or not. So let's say I had something, if I had a box plot that looked something like that. Now notice not every section is the same, right? Most, or 50% of our data, the middle 50% is less spread out than the tails, right? And that's good, because if we have a normal distribution, most of our data is in the middle, right? Between Q1 and Q3. Or it's less spread out, I should say, not most of the data, but it's less spread out. So if you see a box plot or a stem plot or a histogram, where your middle 50%, if your middle 50% is less spread out than the outer 50% and symmetrical, then we can say it's kind of normal. Okay, so definitely check out box plots, histograms. Those probably the two best bets. You could do a dot plot, but you're probably gonna have a lot of data and you don't want to do a dot plot by hand. Calculator is going to be a really good way to do that. Again, I'll show you this using the calculator when we get to an actual problem. Okay. Another way to check if something is normal is by using the mean versus the median. So if your mean is very, very similar to your median, very, very close, that usually means you have symmetrical data. So it's a good way to check if something is approximately normal. And again, we'll look at that to see at a later time to see if that's a good way to check as well, using one of the practice problems. So if the mean and the median are similar, that gives you evidence that the distribution is a roughly normal distribution. So let's dive into some practice. So I got some data from our friends over at Stats Medic. So here's some data from student scores on the AP exam. Now this will be a good reminder too to help create graphical displays from data using our calculator. Once again, to use our calculator to create graphical displays, we're going to want to turn it on. Go to the Stat button right here. Go to Edit. And in L1 is where you want to enter your data. Now, I already did this. I entered in the data before. There are 80 test scores, so you want to make sure, regardless of what data you're entering in, you want to make sure down there, your last data point is your 80th data point. So it says L1, 80. That's good. We want that because that tells us that we have 80 data points in there. With 80 data points, you do want to slow down when entering your data. When I first did this, I was racing a student. She challenged me to see who could enter it faster. We both went really, really fast, and both of us made mistakes. So I want to make sure that you slow down when you do the entering in of the data so you make sure it's correct. Otherwise, you have to go back and find. And the only reason we knew we made a mistake is because when we hit to run the 5-number summary, we got different numbers. So if we entered in the same data and got different numbers, that would never happen. So one of us did something wrong. Turned out it was me. I typed in, I think, like 76 instead of 67. Okay, so now that we have our data in there, we want to check to see first, let's do the mean versus the median. Now remember, if those two are the same or similar, there's a good chance we have normal data. So anytime you want to run any sort of 5-number summary from data, you're going to want to go to Stat, go over to Calculate, one variable statistic, and you want to usually type in where you put your data. So I put my data in L1. So to get access to all the lists, you see the little numbers above the 1, all the L's, that's what you want. So we're going to hit second, and then we're going to hit 1, and you'll see L1 popped in there. Then hit enter. So it's going to give us a lot of stuff. That X bar, you should know that X bar always is the average, right? So our X bar is 79.7. That's your average, okay? That next is just the sum of all your data points. That's the sum of all your data points squared. That's the standard deviation, also the standard deviation. N is your population, so that also tells you how many data points you had. As you scroll down, you'll see the min, Q1, the median, Q3, and the max. So if you notice, my mean was 79.9. My median was 80. Those two numbers are really close, which gives us evidence that this is roughly symmetrical, roughly normal, which means we could use the z-score to get percentiles and all that jazz. That was one way to check it. That was the last way we said, mean versus median. Another way to check it is to actually graph it. So again, here's a quick review on how to graph data. So you're going to want to enter in all your data points like we did. Then you're going to go to second, stat plot. Go into your first stat plot. We're going to turn it on. Let's try a histogram first, right there. Well, where did we put the data? We put the data in L1, right there. So we're going to hit, after all that's on, frequency 1, zoom, number 9. The reason you want to hit zoom number 9 is because that'll zoom in on your data. So if we look at our data, it's roughly symmetrical. We may see a little bit of skewedness, but I would say roughly symmetrical. Again, we can check that using a normal probability plot or our box plot. So that's the histogram of it. Let's try to do a box plot of it. Again, another way to check. So, second, stat plot. Instead of choosing our histogram, we're going to choose our box plot. But remember, these calculators, you can't hit down. If you go down, it's just going to go to the X lift. You have to go right, 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 right. So we'll hit that and then hit zoom 9 again to get our box plot. Ooh, that's showing some skewedness. So now to really check it, we want to actually plot a probability plot, right? So we really want to show that normal probability plot. To do that, again, we go back to our second stat plot, turn it on. This time, you're going to want to go to the very last one. The very last one is our normal probability plot. The data is coming from L1, right, where we entered our 80 data points. The data axis, we're going to use the x-axis as our data axis. The mark is just what do you want it to look like when you actually plot it. It doesn't matter. Just to show you, I'll use the little plus sign. And then again, you're going to hit zoom stat. And we'll see this. So we look at our line, and it's pretty linear. It's not, there's a couple deviations, maybe over, we see a little concavity, not much, but based off of our normal probability plot, this is linear enough where we could use normal calculations to get some answers. Okay, so hopefully that helped you figure out how to use the calculator and how to dive into some checking normality. Because there may be on your test in your classroom, checking normality. We're going to see in our AP problem that there is a question on the AP exam that happened in 2011 where it asks you to check to see if this data seems normal. And we'll take a look at that in a minute. All right, let's move right along. We're going to clear this. And we're going to jump to our AP problem, which comes to us from which one looks better? We'll use that one. My printer is running out of ink. And our school's too broke to buy ink, so I have to buy it on my own. But we can use this for now. So This is the 2011 AP Stat problem, and this is problem number 1. And let's take a look. It says a professional sports team evaluates potential players for certain positions based on 2 main characteristics: speed and strength. So we're looking at, well, how fast are they and how strong are they? Speed is measured by the time required to run a distance of 40 yards, with the smaller times indicating more desirable or faster speeds. From previous speed data for all players in this position, the times to run 40 yards have an average of 4.6 seconds and a standard deviation of 0.5 seconds, with a minimum time of 4.4 seconds, shown on the table below. Based on the relationship between the mean and the standard deviation and the minimum time, is it reasonable to believe that the data is approximately normal? So we want to know, based off the data that we see, is it reasonable to think that this is approximately normal? So there are a couple ways we can tackle this problem. First, let's draw a box plot. Or I'm sorry, let's draw the normal curve. So if this is normal, it should look something like this. With our average here, 4.6, standard deviation, 0.15, and it said our minimum value, was 4.4. Now remember, your minimum should be a very, very extreme number. So if we use the empirical rule, that will help us determine if this is normal. Empirical rule is the same as the 68, 95, 99.7 rule. So that essentially means, I see we got one person in here. Jason, good to see you. Feel free to stop me. We're doing the 2011 AP Stats free response question. So that tells us if I go out 1 standard deviation from my average in a normal distribution, I'm going to cover 68% of the data. So this is add standard deviation. This is subtract a standard deviation. This would be 68% of my data. So 68% of my data should fall within, well, if I do 4.6 plus 0.1, that would be 4.75. And this would be 4.45. Again, this is seconds based off of their running times. If I go out another standard deviation, so I add another standard deviation, I should be at 4.9. And if I subtract another standard deviation, I'm at 4.3. And that covers, or should cover, 95%. Then, if I go out one more standard deviation, so I'm at 4.15, and I'm at 5.05, I believe if my mental math is correct, I would cover 99.7% of the data. So my very, very extreme, or my lowest values and my highest values, should be the only things that really fall outside. But let's not forget, they said our minimum value was 4.4, which is right about here. Now, there's still, almost said hella data, there's still a lot of data if it was a normal distribution below that number, below the minimum. So that gives us pretty strong evidence that this distribution of run times is actually not normal. It's maybe skewed to the left or skewed to the right, but it's not normal, because if it is normal, we would expect a minimum to be down here. We would expect our minimum to be maybe around 4.10. But since it's 4.4 and our average is 4.6, they're too close. There's not enough spread here to say that this is normal. And let's take a look at what the actual answer said. So here's our answer. This is like the perfect answer that you would want. No, it is not reasonable to believe that the distribution of 40-yard running times is approximately normal, because the minimum is only 1.3 standard deviations below the mean. They did their calculations here. In a normal distribution, approximately 9.2% of z-scores are below negative 1.33. However, there are no running times less than 4.4, which indicates that there are no running times with a z-score less than negative 1.33. Therefore, the distribution of running times is in fact not normal, right? And so that's what they're talking about down here, is they're saying there is no way that this can be normal because our z-score is too low. I'm sorry, our z-score is, or our data point is not low enough, I should say. So that's a great way to tell if something is not normal, if a distribution is not normal. Okay, let's go to part B, because part B also has to do with this chapter, and I think it might be important to take a look. And again, if you have any questions, pop them below. We're doing the 2011 AP Stat question. All right, part B. Strength is measured by the amount of weight lifted, with more weight indicating a more desirable, greater strength. From previous strength data for all players in this position, the amount of weight lifted has a mean of 310 pounds and a standard deviation of 25 pounds, as shown in the table below. Calculate and interpret the z-score for a player in this position who can lift a weight of 370 pounds. So I always encourage my students to make sure that they actually draw this distribution and the normal curve. When you draw it, you actually physically get to see it, and it kind of allows you to make a little bit more sense. So if I draw my distribution, draw my average, .310, standard deviation of 25. So, and just they should mention that this is a normal distribution, because we can't do z-score calculations if it's not normal. We're going to assume that it's normal since they're asking us on the AP exam, but you need to make sure that it's normal in order to do any of these calculations. So in order to find z-score, don't forget your formula. We're trying to calculate and interpret the z-score for a player whose position can lift 370. So 370 is going to be above the average. We're looking for this z-score. So to do that, we're going to use our z equals your data point minus the average divided by your standard deviation. So z equals 370 minus 310 divided by 25. All we did was plug in there. So we get z equals, that's going to be 60 divided by 25. So we're going to get a z-score of 2.4. Now that's good that we got a positive number, because it's above the average, right? If we got a negative z-score, that means it would fall below the average. So we found our z-score. That's great. That would get us full credit. Now we need to interpret our z-score. So in order to interpret your z-score, we have to know what z-score means. Now again, the z-score tells you how many standard deviations away from your average and in what direction your data point is. So in this case, we would want to say a z-score of 2.4 indicates that the amount of weight, we want to put context in there, the player can lift is 2.4 standard deviations above the mean. And if we wanted to be a little bougie, we could say for all previous players in this position. So I want to stop for a second because this type of sentence can just be interchanged with whatever context you're talking about, right? So anytime you want to interpret a z-score, you could just use this as like your stem, right? Is blank standard deviations above the mean. That's all you really need to know. It's below or above the mean, right? So if you have a negative z-score, instead of above, you're going to use below. But z-score just tells you how many standard deviations from the mean your data point is. All right. Let's move to our next question. Letter C. Sorry, it's tough to see, but I'll read it for us. The characteristic of speed and strength are considered to be of equal importance to the team in selecting a player for the position. Based on the information about the means and standard deviations of the speed and strength data for all players and measurements listed in the table below for player A and B, which player should be selected if the team can only select one of the two players? Great scenario. This is like, I'm up in Oakland, so the Golden State Warriors are huge. Students love them. The Bay loves the Golden State Warriors. I am unfortunately a Clippers fan, which has been really tough to be up in the Bay for the past 6 years being a Clippers fan. But anytime you're in the draft room, like the Golden State Warriors, they're a pretty good drafting team. But the Clippers are looking pretty good when it comes to the draft. Yes, thank you. So you're in the draft board. You want to know how unusual or how great is this player when it comes to different metrics. So in this particular sport, we're looking at running and lifting. So we have two players, player A, player B. So we want to look at two different distributions and see what we have. So let's look at our two distributions. So the first distribution we have is the run times. And when we have run times, we have our average as 4.6. And our standard deviation is 0.15. Now, remember, run times, we want a smaller run time. So we actually want to be below the mean here. For our other distribution, we have lifting or strength. We have an average of 310 with a standard deviation of 25. Then we have these two players. I'm going to do player A in green. I don't know why I did PLY for player, but we're going to roll with it. Player B in red. So for player A, they have a runtime of 4.2. Sorry, 4.42. And they have a weight lift of 370. Player B had 4.57, which again is going to be closer to our average. But he could lift, or she could lift, 375. Now, that's all great, but we want to use z-score so we can standardize all this to see how much faster is player A than everyone else. In this case, how much faster is player A than player B? Then we want to look at their strength. How much stronger is player A than player B? Or how much stronger is player B than player A? Because if one of them is just a little bit stronger, but maybe has a much better head on their shoulders, maybe I want to draft that person. But if the person is just like ridiculously strong and I don't know, we're doing football and we want to have someone block or pass rush, we want to make sure that we get that person because they're like out of the ordinary, they're extraordinary. So to do that, we use our good friends at z-score. We want to find the z-score and the percentile for each of these players and their distributions. So we'll start with player A and the runtime. So we're going to say Z equals their score minus the average divided by the standard deviation. When you do all that, we actually get a z-score of, this is for runtimes, so negative 1.2. And if we do it for player B, we get Z equals 4.57 minus 4.6 divided by 0.15. So we get a z-score of negative 0.2. So right away, we can tell player A is a little bit better, is one standard deviation better than player B. Now let's go over to our strength. So strength, my z-score for player A is going to be 370, take away 310, divided by 25, which is going to give me a z-score of 2.4. Now let's use player B. Again, z-score equals their score minus the average divided by the standard deviation, and that's going to give me a z-score of 2.6. So now we can compare. Now we have a good idea of who did better based off of standardized scores. So if we see running times, player A was one standard deviation better than player B. That's pretty significant. One standard deviation is quite a lot. Over here, when it came to strength, player B was the better one. But he was only 0.2 standard deviations better than player A. So if we're thinking which player do we want to draft, we probably want to go with player A. The reason we think player A is going to be a better bet is because player A is significantly stronger than player B, right? One whole standard deviation. When it came to strength, player A was just a fraction, or it was just 0.2 standard deviations worse than player B. So player A was a much faster runner than player B and was just a little bit weaker than player B. So we would want to go with player A because they are much faster and just a little bit weaker. Player B is stronger, but not by much. And when it came to speed, they were a lot slower. So we would want to go with player A. Jason, any questions on that one? Are you in section 2 still? Shoot me a question or email. Okay, cool. Appreciate it, Jason. Are you still in chapter 2 or did you move on to a different chapter? Cool. Did you have an actual, well, we can talk later. We're going to move on to chapter 3, which is what you're probably getting into. Is that right? Correlation, linear regression. I will be here next week. I'll actually be in San Diego, but I'll be doing this next week for y'all. I'll be at an AP stat training. So definitely help you out with that as well. And if you want to stick around and just kind of type anything that you're working on, I can definitely tailor this to your needs for the next one. But I'll be going over chapter 3 next time. So we'll dive right into that. Get you a nice head start. In the meantime, thanks for sticking with me. Hopefully you found this helpful. As always, these live sessions are going to be way more helpful for you than the replays. The replays are definitely going to be helpful, especially when it comes to the AP exam. But these live sessions are great for asking questions, for engaging with other students. So please, please, please make sure you come to these live sessions because they're great. And you can ask me questions. That's what I love about this job. Stick around. Next week, we'll go over chapter 3, which is all about linear regression and bivariate data. So bivariate meaning 2 pieces of data instead of just one. Like right here, all I had was runtime. That's 1 piece of data. But if you have maybe runtime versus age, that's 2 pieces of data, and we want to analyze that to help us out. Thanks. As always, go to Fiveable, register there. If you do it now, you're going to save a whole bunch of money when it comes to September or when it comes to May, I should say. And you won't be procrastinating. And no one likes to procrastinate. All right. Appreciate your time. Thanks. I'll stick around if you have any questions. In the meantime, we'll see you next week.